The last set of material for the semester is eigenvalues, eigenvectors, and diagonalization. So it's a short set, and it's not necessarily exactly solving systems of equations, but we're looking at eigenvalues, which are useful in certain applications. So when we multiply a matrix by a vector to get another vector, essentially what happens with three-dimensional space is we're moving that vector to another location. So if I look at 2, 1 here, so here's V1, and I multiply it by this A matrix here, I essentially moved it to 0, 5. That's what happens when we're doing matrix multiplication with vectors. It's called a transformation, where we're moving vectors in space from one location to another location. Well, there are certain matrices that when we multiply a vector by that matrix, all it ends up is if we scaled it in the same direction. So essentially, if I take A times X, it's equal to some constant times X. So rather than V2 being in a completely different location, it would essentially be a scalar of V1. So essentially maybe 4, 2. This one obviously does not do that, but that's essentially what it looks like. It appears as if A V1 is just equal to some constant times V2. That constant is what we call lambda. It's an eigenvalue. So what we want to do is we want to go ahead and figure out which eigenvalues and which eigenvectors, so these x ones here are eigenvectors. So we want to figure out which vectors this happens to and what their scalars are, what my eigenvalues are. This is called the Eigenvalue Problem. Essentially, figuring out which vectors this scaling appears to occur for. So the Eigenvalue Problem is essentially stating that ax equals lambda x. When I multiply a by a vector, it just appears as if it's scaled by a constant called lambda. If I rearrange this equation and I move this to this side, I end up with this situation. Factor out x. I end up with a times lambda identity, so here's identity, equals 0. This type of system is called a homogeneous system, which means my b vector is 0. It turns out that for this system, my solution is only the trivial solution, where x equals 0, which means that a is going to be, or the determinant of a is going to be non-zero, and a is invertible. Okay, so if the determinant of a is not equal to 0, a inverse exists, but my solution is only ever going to be 0. So that's this scenario. If I have a solution, my solution is always 0. That's not really interesting. We don't really care about the one where my solution is always ever equal to 0. So what we care about is if the opposite occurs when we have the non-trivial solution, where x is not equal to 0. This will occur if my determinant of a is equal to 0. So I have two options. My determinant is equal to 0 or not equal to 0. If it's not equal to 0, my solution is only ever x equals 0. We don't care about that one. We care about when we have determinant of a is equal to 0. And it turns out if the determinant of a is equal to 0, we'll have an infinite number of solutions. Yeah, so this is going to frame essentially how we find our eigenvectors and our eigenvalues. The first thing we can find is our eigenvalues. So my eigenvalues I'm going to find by using my determinant. So we know that we're only interested in this situation where the determinant of a is equal to 0. So what we're going to do is we're going to look at the system. A minus lambda I, x equals 0. This here is essentially just a way of saying A. It's just A minus another matrix. So this is just a matrix here. So I'm going to set this determinant equal to 0. What happens when I do that is I end up with my unknown, which is lambda. So one equation, one unknown. I can go ahead and solve for my lambdas. When we do this, we typically end up with a cubic polynomial. Not always, but we generally end up with a cubic polynomial, so it is a little bit more challenging to factor, but we do end up with our individual lambda values. And then, once we can find all of our eigenvalues, then I can go ahead and plug it into my equation up here to solve for my eigenvectors, or solve for my x. So my eigenvectors can be found by solving the system of equations here, where I already know what my eigenvalues are. In general, we have a cubic polynomial, so we have 3 eigenvalues. Not all the time, but some of the times, which means we need to solve this 3 times. Every time we solve for this, we are going to get an infinite number of solutions. So the best method we want to use in order to solve that system is Gauss-Jordan elimination. Because every time we solve for it, we get an infinite number of solutions because we've made our determinant here equal to 0. Which means each eigenvector is going to be an infinite set of values. We generally choose the smallest whole number vector that is listed. Okay, so our process for approaching eigenvalue and eigenvector problems is first solve this here. I forgot to mention this is the characteristic equation. And that's our name for it, the characteristic equation. Set the determinant of a minus lambda I equal to 0 and solve for the values of lambda. Then for each lambda value, so generally we get 3 lambda values, at least 3 for a 3 by 3. If you have a 4 by 4, you would get 4. If you have a 2 by 2, you get 2, etc. And then for each lambda value, we're going to go ahead and plug it into our equation, a minus lambda I, x equals 0. Solve that system using Gauss-Jordan elimination. This is your augmented matrix. Then we're going to end up with an infinite number of solutions. Choose a value for your arbitrary parameter to write the smallest whole number eigenvector. And that's how we're going to solve our eigenvector problem in order to find our eigenvectors and our eigenvalues.